Testing, testing, 1, 2, 3.
MES, an expert system for reusing models of transmission equipment. I'm going the wrong way, I think.
Can everybody hear me pretty well there in the back? Holler if you can. The particular department and laboratory at Bell Labs that I represent is responsible for developing systems that are used to monitor and help expand and design the AT&T transmission network. And before we talk about the particular expert system that we've designed to automatically generate transmission equipment models, I'd like to give you a brief background of where these models end up and how they're used. Okay, TERX, which is the acronym for Trunk's Integrated Record Keeping System, is a very large system that runs on a mainframe and is used by the transmission engineers to provision circuits. It has over 200 databases. It's been under development now for well over 15 years. It has over 8 million lines of source code. Sure, it's a very large system. One of those modules provides specifically transmission performance of a particular circuit, and that module is called compute. It is in compute itself where these models eventually reside and are being used. Okay, the standard design, circuit design system itself uses many equipment and facility databases. It also uses circuit inventory type databases, and along with order entry information, designs the circuit by simply taking a point A and a point Z anywhere within a geographic location. If the user then describes the type of facility that they would like between these 2 points, the module called CDS, or Circuit Design System, will design all of the transmission equipment between these points, utilizing that facility that is required in order to provide the service. The compute module then looks at every piece of equipment along the transmission path, and it sets or adjusts all of the specific equipment to make sure that optimum transmission performance is obtained. Now, compute does this by using models of the transmission equipment. By a model, we mean a representation of a 2-port device, which basically has an input and an output, some type of transmission transfer function. In our particular case, the input and outputs are voltages and currents to each piece of equipment that are linearly related by A, B, C, and D variables, and you can represent the input and the outputs in terms of a matrix equation involving the inputs, the outputs, and this matrix, which we call the ABCD matrix or transmission matrix. The specific A, B, C, and D parameters are complex variables which are dependent upon the equipment or the specific components of that network. They are frequency dependent, and they are also dependent on the physical state of that network itself and all the switches there. So A, B, C, D in itself can be very complex type numbers. Well, if we can, and we do, write routines or programs that describe in detail what this A, B, and C, and D parameters are at all physical states of this network and at all frequencies within the voice band, 0 to 4 kilohertz, then we've essentially defined a model for this specific piece of equipment. Now, in compute, most of these models have been written in PL1. And the way they're used by compute is to simply say if we want to calculate the performance between a central office and the Z end of a transmultiplexer, compute will then recall from its databases the ABCD parameters at the particular frequencies for the equipment that is between the A and the Z points. In this case, the central office, the D4 channel unit, T1 carrier lines, and so forth. At the present time, there are well over 300 different types of models of equipment that are being used by compute. Each one of these pieces of equipment then has an equivalent independent matrix representation, and because of the linearity of the system, these matrices can be multiplied, and an equivalent matrix can be derived for the entire circuit end to end. From this transmission matrix, we can then derive the performance parameters that are necessary to analyze the circuit performance. The way we describe a circuit to compute is via a description language which uses each line of a file as a specific circuit element. In this case, a circuit like this we would describe as a pad, 4-wire of 0 dB loss. Subtype 1 would indicate that that's a central office as opposed to a PBX or any other transmission switching type terminating element. For the D4 channel unit, the representation, input representation of that would look like this, where we specify that this is a transmission-only unit oriented in the A to B direction. The transmit attenuator is 6.5 dB, the terminating impedances are 600, and so forth. In that fashion, we describe the entire circuit. Now, given that circuit description, for every circuit element, or every circuit family, there is a series of subroutines or programs, again, all written in PO1, that parse the first name of the equipment, make sure that that equipment is indeed available. It parses the option settings on the device itself. It also calculates the ABCD matrix. The sub-26C routines calculate the ABCD matrix for that piece of equipment. And then we can also initialize the equipment itself, the internal representation of this equipment, with other programs shown here by init before. There's a whole family of those. There are also other routines that calculate outputs and provide equalization and gain distribution along a transmission path. Now, all of these programs are essentially used to model the equipment itself. The output parameters are then parameters such as losses, delays, impedances, and so forth. Models can be of two types. They can be data-driven or algebraic form type models. By a data-driven model, we mean essentially a model that has been obtained by extensively taking measured data on a specific piece of equipment. And we do have models that are of that type, namely the transmultiplexer and digital access cross-connect systems, DACs. The algebraic form type models are models that we can simply generate or describe their ABCD matrix by simply looking at a schematic of these pieces of equipment and performing a nodal analysis on them, determining the ABCD parameters in closed form. Now, immediately after divestiture, what our department found was that we were getting requests for non-Western Electric at the time, or non-AT&T equipment was being introduced into the network, and we were getting a lot of requests for models of this equipment. And what we thought was that essentially, rather than to develop these models again from scratch as we had done in the past, that perhaps we could go into the databases of the existing models that we had and simply fine-tune these models so that they would provide an adequate simulation of the new equipment. And we thought that if we can then codify this knowledge and automate it, then perhaps we can implement it with an expert system. And this is what was the primary motivation for MES, or the modeling expert system. That we essentially wanted a system that would aid in the development of the PO1 models, and we used the concept of cloning, or essentially taking a model that existed and resided in our databases, and from it derive something new. And we found that the knowledge to be able to do this was very ill-structured. It was known to only a few experts. That was primarily because it cut across many domain or areas of expertise. An individual would have to know about transmission equipment, PO1 programming, and the compute application itself. And we also wanted to be able to preserve this knowledge, and while reusing a lot of the software that we had, speeding up the model development process, which at this time was somewhere in the order of 2 to 3 months. We also wanted to standardize the process to make sure that all of our models were not only being generated productively, but also in high quality standardized form. Given those requirements, we came up with a system that has essentially 2 functions and is now being utilized, but it has gone beyond the prototype phase. In the first function, the clone determination phase, the system prompts the user for information about the particular piece of equipment that they would like to model. And through a reasoning process, decides whether we do have or whether we don't a model in our database that can be used, or a series of PO1 programs, in essence, that can be used as the basis from which we can generate a new model. If that is the case, then the second function is invoked, and the user can then automatically generate code by simply taking the existing models that are in the database, applying a series of strategic changes to that source code, and generating a new model for that equipment. The code manipulation is essentially generated, it has to all be generated in PO1. And this is a specification sheet of a particular piece of equipment, in this case a D4, which the user would use. Now in this case, the user would know that this D4 channel unit, let's say, has a transmit attenuator with values between 0 and 16.5 dB. It also has a receive attenuator, that it has an equalizer with bandwidth, height, slope switches, and so forth. Now this is the kind of information that would be used, or the system would prompt the user for, in order to determine whether a clone can be made. During the code generation phase, for D4 specifically, code has to be changed at 25 different places within about 15 or so PO1 source code files. And these changes are of 2 types. They are changes that basically require for us to generate a line of code or an entire block of code and insert it within the source code, or changes that simply require the modification of a line or a block of code, editing the existing lines of code. This is the equipment that thus far we've been able to, that the system knows about, that the system has in its knowledge base and can create clones from D4 channel units and transmultiplexers. And because D5 channel units are also derivatives of D4, the system can also, not shown here, can also clone D5 channel unit models. During the clone determination phase, the rules that are used are of this format. For example, if a unit is a D4 as opposed to a transmultiplexer or another type of unit, and the unit has an equalizer, and the equalizer has a bandwidth, height, and slope switch, then we can use the 4FXO, 4FXS, 4DX, or 4ETO units as basis models for our clone. Another example of a rule is that if the unit is of a D4 type and it has an attenuator, transmit or receive direction, and the attenuator range is between 0 and 6.3 dB, then the 4 PLR unit can be used as the basis. Some examples of editing a line of code shown here. Let us say that we want to add another channel unit now. Once we've determined that we can clone a new D4 channel unit, we want to add new model to our database, we may want to have to indicate that there are 28 legal names now instead of 27, so that may require this number to be changed. And if this unit has an equalizer, then we may have to go into another line of code in a different part of the program and change the 14 to a 15, indicating that there are now 15 units of 15 total models that we can use to provide equalization. Now the knowledge, the information that's needed in order to generate code for to create the clone is information that's either supplied by the user during the clone determination phase or derived during this phase, again, from information that has been supplied by the user. Another way of using information or derived information for the code generation is to simply look at the source code and from it derive information. For example, if these were 2 lines of code here in the file, in the existing source file, and we wanted to add another D4 channel unit, we would have to add a 3rd line here, initializing the value here to 417. So the system would have to go through the existing file and note that 417 would be the next available number in this line. It would also have to change the semicolon to a comma to adhere with the PL1 syntax. And to do this, we basically would provide a template that would look like this, and in this template we would insert here the unit name, the name of the D4 channel unit that we're trying to clone, and we would have a 417 already updated, and any other documentation that we wanted to add in the code would go here. So in addition to information that's extracted during from the code itself, we can also extract information from the user during the code generation phase. And the code generation itself, that entire process is a template-driven process. This is an example of a template. If we wanted to generate a new line, single line of code, our template might look something like this, where the when, the if, and the then return would be constant values, and the values here in the brackets would be variables that are going to change and eventually become a part of the code. That information would come from any one of the methods that we previously just described. This is an example here of a block of code. Again, in here we would have the name of a procedure or the unit name, and if the unit had an attenuator and or a receive attenuator in transmit or receiver direction, we would have 2 lines here, one for the transmit direction and one for the receive. And if we wanted to return a particular value, we would have that value here, and so forth. Look at the process of how code itself is generated. Essentially, we go through a series of steps. We look at the source code itself, and we find the line number where the code is either to be added, the new code is to be edited, or information from where we need to extract, a line number from where we need to extract information in order to generate the code. After finding that line number, essentially we do that by using a Unix facility called awk to do a lot of pattern matching. And one of the problems that we found in developing the system of this type was that because code itself, source code, is usually under some stringent, which was the case here, of control, we had to make sure that manual control of that code did not affect any markers that we would place in the code that are going to be used or are being used by the system itself. So what we found was that the minute we added markers in the code, in the source code itself, so that the expert system knew exactly how to traverse through the source code in order to modify it, if we didn't keep good tight control on that code and someone came in and took those markers out in the process of maintaining that code, we could possibly then perturb the code. That code would no longer be able to function the way it should within the system. So in essence, all of the code, as we developed the system that was being used by the system, we took out of manual source control and made sure that the code itself was being updated by the system. Once we find the line number, we then use list functions, a series of list functions, to make the actual changes and to generate the actual code itself. We also used said filters in order to insert and replace or replace old code or new code, inserting new one and replacing old one. And again, for this, we used list and set. In essence, we tried to apply the best of both list and Unix. Some of the system highlights are that it does not the system itself will ask questions based upon responses that have been given by the user of previous questions. And it'll stop right away if there are any hypotheses that are eliminated. In the meantime, the questions themselves are used by the system to eliminate a lot of the hypotheses or the possible models that can be used by the system. And the questions that are asked are context sensitive. If the system, for example, if we respond to the question, does the unit have an equalizer? If we respond to that no, then the system will not ask us, does it have a bandwidth height or slope switch? And there are also explanatory type information that we thought we'd add for some of the novice model developers that allow the novice user to query the system to find out why it's asking certain questions, and also to probe into its reasoning process and be able to trace why it did certain things. Now, a bit about the size of the system itself. There's about 120 or so OPS5 rules. We decided on OPS5 because we wanted to be able to deploy this system in as inexpensive fashion as possible, and we found that using OPS5 allowed us to do that. We didn't have to go to dedicated hardware. There's about 1,000 or so lines of list codes, 25 awk procedures, and there's a series of set scripts that are being used by the system. So far, we found that we've been able to, with this process, reduce the model development time, and in essence, the time it takes to integrate these models into the system. We've been able to reduce that from about 2 to 3 months to a little under 2 or 3 days. And most of that time is spent by the user, the novice user, learning about the particular piece of equipment, transmission equipment that we want to model in order to be able to correctly respond to the system. That's essentially the modeling expert system. If there are any questions, I'm more than happy to answer them. I think I see one at the back. Yes? I'm sorry, could you repeat that, please?
There were comments on the code that you are modifying.
Yes.
Do you have any intention of preserving them?
The comments?
Yes.
Yes. I believe you're asking if there are comments in the code itself. Do we keep those comments there?
Yes.
Yes, we do. We only make the modifications in the code itself that are necessary, so that even though the code is being maintained now in an automatic fashion, we don't remove the comments that were previously there. Any other questions? Thank you.